was a popular speaker at the 2012 EU, and he's back. Electrical engineer with degrees in mathematics and physics, formerly of NASA, the originator of the extinction shift principle, which challenges the general and special theories of relativity. Let's welcome Dr. Dowdye to the stage to challenge us a bit.
The title of this is continuation of what I have done before. In this talk, we talk about solar gravitational gradient interacts directly with electromagnetic waves propagating in the solar plasma limb. And when I say the gravitational gradient, for an example, we know very well that when you put up satellites in the deep space, you put atomic clocks on board these systems. In order for the GPS system to work properly, each one of these platforms that are orbiting about the Earth has to be timed. A time reference has to be on board the system in order for when you receive a pulse in your vehicle and you're moving on the ground or in the air, you know your exact location, because when you receive that information from these GPS systems, they time tag it, and the clock running on board the satellite has to run at the same rate as that on Earth. But the problem here is when you put these systems in space, the gravitational gradient acts on the atomic clock, and actually the clock on Earth would actually run at a slower rate than the one in space. So let's talk about this. So in the next 19 minutes, I'm just going to give you a split on this. So I'm going to go to the next slide here, which is similar to this slide. My title is actually the solar gravitational gradient acting on the electromagnetic waves. Turns out that the solar gravitational gradient interacts directly with the solar plasma limb, but the solar plasma limb interacts directly with the electromagnetic waves. But however, the gravitational gradient, the first one, interacts indirectly with the electromagnetic waves. So that's the gist of what I'm talking about here. And there's enormous evidence for that. And relativity, the people who support relativity are fighting against this. So let's go on to the next one. Here's a picture of what I mean from the first two slides. See, you have the solar rim of the sun. And it turns out that the solar rim of the sun contains hot plasma gases. We've been talking about plasma for the last day here and partly yesterday. The plasma is actually totally ionized of the sun. The ionized rim of the sun is such that the particles in this rim are ripped up off the electron clouds, so you have only nuclei of your positive and negative nuclei. So it's actually a plasma about 5,000 to 6,000 degrees Celsius. And it turns out that that plasma rim is being acted on by the gravitational gradient of the sun. And it has a gravitational profile. And when light propagates through that, or microwaves or whatever waves propagates through it, you can determine the path of the waves propagating through that. And there's a calculation that allows you to get that. And what happens, this plasma limb of the sun acts directly on the electromagnetic waves propagating along the minimum energy path. It turns out that you send your students, you get your students assignment in undergraduate and graduate classes, and you guys, you know this because I'm preaching to the choir here. You talk about the minimum energy path or the least time path of waves propagating in an atmosphere or some medium along a minimum energy path, and it would be defined by the gravitational gradient field of the sun. And it turns out that the gravitational gradient field of the sun acts only indirectly with the electromagnetic waves. So let's go on and see what we're talking about here. Here we find out if you go above the solar rim in space, going above that solar rim, as long as you're in the rim, there's bending taking place in the rim. But above that, several of even a fraction of a solar radius or mini solar radius above it, it turns out that electromagnetic waves propagate in the plasma-free space, the space where you have no plasma at all. There's no bending. And these light rays are going along a straight line path. So the next slide, continuing on, showing a picture again. You have the solar rim, and it turns out you have the sun The radius of the sun approximately, 650,000 kilometers radius. So actually what happens above the solar rim and beyond that, engulfing almost all the planets orbiting about the sun, there is an electron profile, and it's what's known as a solar wind. And I'm going to talk about that later on very briefly because we don't have very few time there. So what's happening, if you have a satellite system, a system moving down, back I have a pointer, and I'll point to you what is meant by a point here, going down. Let's say you have a system moving down, a satellite system moving down. It could be the Earth or a planet moving from here on down. What happened, this system contains antennas on board, and the antennas are such that they're spread apart so you can have a wide beam, what is called a wide beam interferometer, wide beam interferometer system. And this system will detect the rays of light coming from a distant source. And this distant source is so far over here that these rays are almost parallel with one another. And what happens is when one of those rays interact with the solar plasma of the sun, there's bending that takes place. And in a star like the sun that has one solar mass and one solar radius would bend 1.75 arc seconds. So that's just bending down 1.575 arc seconds, right? And in the ray that goes on the other side of the sun would bend up. So it turns out that this bending is such that the sun acts like a lens, and it acts pretty much like a lens here, whereby if you go far enough away from that, way out here someplace, these rays will come together and come to a focus. But that's a long distance. Let's talk about that later on. But what's taking place here, you can detect the bending. This would bend up, and this one would bend down. But in the middle here, there is no field. As if this information that's coming from this distant source, some radio, could be a radio source or some satellite system or a distant quasar system that is emitting microwaves, these rays are noticed to bend. And what they had, the astrophysicists had measured always this 1.75 arcseconds. But however, there has been no information up here at all or down here. That means the bending always takes place at the plasma rim of the sun. That is in itself a direct violation of general relativity. And there's enormous evidence for that, and I'll show you the evidence that's taking place after this. Let's take a look at what do we mean by gravitational gradient. If you look at the gravitational gradient of the Earth in comparison to that of the sun, if you look at the sun, for an example, if you are just above the surface of the sun, there's a gravitational potential, a very strong gravitational potential. And if you're over here above, you go to 0.38 astronomical units, 0.72 astronomical units, there you have Mercury and you have Venus. And 1.0 astronomical unit, there's the planet Earth. On the Earth's surface, it turns out that the gravitational potential of the sun is almost a factor of 14 times greater than that of the gravitational potential of the Earth. But that is the gravitational potential of the sun. This yellow line indicates the gravitational potential of the sun. But however, that little box where you have the Earth, 1.00 astronomical units, if I blow that box up, I have the planet Earth here, and you calculate what is known as the gravitational potential of the Earth. The green line represents the gravitational potential of the Earth. But down below, you have blown up in this box the gravitational potential of the sun, indicated by that yellow line down below. That's 14 times greater than that of the sun. But it's not the gravitational potential that we're concerned about. We are concerned about the gravitational gradient, not the gravitational potential. The gravitational gradient is the key here. So let's take a look at this next slide. If you note the gravitational potential of the sun and the Earth, at any given point in space, the sun always wins over. But the gravitational potential gradient, that's a different story. But you have the sun, the gravitational potential of the sun, V sun, is equal to approximately 14.14 times that of the gravitational potential of the Earth. That's key. Keep that in mind. But the next time, we're going to do we look at the gravitational potential gradient. If you calculate the gravitational potential gradient, what you have to do is take the first derivative of the sun, the gravitational potential of the sun, along a z-axis. And z coming from the sun, where you have the radius of the sun is 1 astronomical unit. The radius of the orbit of the Earth is 1 astronomical unit. If you look at that at the Earth, right, you'll find that that is much smaller than the gravitational potential of the Earth for along a radial path, which is the radius of the Earth. So that's significant because you find out why is it the atomic clocks run slower when you put the atomic clocks in space than on Earth. It turns out the moon has a profound effect on the Earth's tidal effect. The tidal effect causes the waters to stand up on a hill when the moon passes above the Earth. It is the moon that wins over when it comes to gravitational gradient of the moon. It's greater than that of the gravitational gradient of the sun. But however, the gravitational gradient of the Earth is far more than that. So going on to the next slide, I'm going to try to sum this up in the next 10 minutes. So making the picture short, taking the sun, the gravitational gradient plasma rim of the sun, you'll find that history for the last 100 years now, the scientists have been able to measure light bending of the stars in the gravitational rim of the sun. But if relativity were factual, according to general relativity, light bending should be everywhere where you have gravitation. But that is not the case. The scientists who support relativity, this is bad news for them. They don't want you to know about this. So let's this next slide. This is the prediction of general relativity. Relativity says there's bending at the rim of the sun. At the rim of the sun, you have 1.75 arcseconds bending, but above that, if you go a radius twice the solar radius above that, the bending should be 1/2 of that. In other words, it's 1/2 of 1.75 arcseconds, or approximately 0.85 arcseconds. And above that, 3 solar radii above that, it's 1/3. And then you get 1/4 and 1/5 and so forth. That's general relativity. But what happens here, that relativity fails this experiment. So you take the general relativity equation, which is the light bending 4 times gm divided by rc squared. That is the bending predicted by general relativity in the units of radians. You can convert that to arcseconds, but 2 pi radians is 360 degrees, and 1 degree is 3,600 arcseconds. You work out the mathematics. That first equation should get you 1.75 arcseconds. But you take the Earth and the sun, the mass of the sun, and let that be m, and no matter what the potential, what the density is that mass happens to be, using Gauss' law, you should get exactly the same bending. So using Gauss' method, you can show that using Gauss' method, you can find a lot of objects out in deep space where relativity has failed. And going forward, we can use the principle of reciprocity and the principle of Gauss, showing these 2 principles that are in textbooks all over the planet now. We teach this stuff in astrophysics, in general physics, undergraduate physics. The students are learning this stuff, but however, they're not tying it down to the failure of general relativity. They keep that solid. So this is our job, to point this out to these guys. You point out the failure of relativity. So going forward and summarizing what I just talked about, you have 3 different masses. If these masses are the same, they could be more dense, enclosed within a Gaussian sphere. We come up with the same light bending, and the optical reciprocity is illustrated here. So let me move fast. And this summarizes what I just talked about in the previous slides. So I'm just going to move forward. So as a matter of fact, I will summarize this in the next couple of days if you want a summary on this. So let's look at this. Summarizing, again, the principle of reciprocity, what we just talked about. If you have bending of a star, and so you have a star that is a distance beyond the mass that's responsible for light bending, and you are the observer at the telescope, you should not see, according to general relativity, you will not see a point light source. In other words, you should see bending all around, and this is looking at it in 2 dimensions. Looking at it in 2 dimensions, you see the bending for light coming from the star, bending up, and then going down to the telescope. The light beam could also go in the other direction and go down first and then bend up toward the telescope. If that happens, according to the prediction of general relativity, the observer should see an Einstein ring. And the Einstein ring should be visible anytime you have this picture. So let's go forward and take what we have here. I started to put in picture an animation of what actually takes place when you have a distant light source out in deep space. That light source could be a red light source, where you have the photons of light or wave packets coming from light. If we don't need the word photon, we can use wave packets, or we can use just emissions of optical waves coming from a red light source. And if in the center between that light source and our telescope, if there's some object in the center that is, according to general relativity, could cause bending of light, that light should be reflected or amplified or actually magnified by the massive light source halfway in between, and the observer should see in that case an Einstein ring. And down below, just below the observer in his telescope, this is what the observer should be seeing in his telescope. He should see a red ring around that red X instead of seeing a point light source. So let me move on and try to summarize this as we go past. The main key here is the gravitational light bending as a function of the impact parameter in plasma-free vacuum space. This is the main thing we want to talk about here. So what I did, we talked about the light bending as a function of the impact parameter. The smallest impact parameter you can have would be that of the radius of the sun. So I can go to two solar radius, or I can go to 3 solar radius, or 4 solar radius, or 5 solar radius. If you go on beyond, the light bending should get less and less. So let's take a look and see what we have here. So you take a look at what the reality tells us. For the last 100 years of observation, we have observed virtually no bending at all of starlight beyond the solar rim of the sun. So if you go back and look at relativity again, relativity predicts bending whether you are at the solar rim or beyond the solar rim. But however, the reality tells us this: the impact parameter beyond the sun, there is no bending whatsoever. So here relativity has a problem. So looking at this, summarizing what we're seeing in the picture, the solar bending, the solar limb of the sun causes 1.75 arcseconds of bending, where there's no bending above that. So we take a look at the light bending as reality tells us in deep space. Modern astronomers should tell us, should be able to explain this at all. So we have 2R, 3R, 4R, NR. There should be a bending always according to general relativity. So, and going back again, what we talked about, if the sun bends light rays, and it has always been the dream of some astrophysicists to go into deep space and take a spacecraft and travel out and find a point in space where the sun bends light rays and they come to a point. It turns out that if you take the 1.75 arcseconds in the radius of the sun and go out beyond space, you should go at least 550 astronomical units. That is 550 times the orbital radius of Earth. And that's not likely right now because of the space program we have right now. It's not silent. It's maybe in some time in the future, I'm not going to be here. Maybe my kids or your kids, maybe some of you guys are younger than I am, you'll be here. So that's not going to happen right now. So here is the data looking at for the past couple of years. I have managed to publish some papers in the Refraction journal calculating the impact parameter at the impact parameter, the solar radius. You calculate the minimum energy path, you'll find that you come up with an equation that will tell you at one solar radius what that bending would be. And I come up with the very same equation as that of general relativity, but it has nothing to do with general relativity at all. So let's go forward, and I'm going to try to summarize this in the next 5 minutes, and I'm done. There's a principle known as that of the Shapiro delay. And the Shapiro was a scientist who used Mariner satellites that was put up by the government, and they used microwave transmission and communication with these Mariner satellites. And we had orbited around Venus. There are some orbiting satellites around Venus. And when I was at NASA, I had a neodymium YAG laser. And one of my projects got canceled. These guys took my laser and used it at the astronomical observatory to try to hit Venus with neodymium YAG lasers. I had this 1,000 millijoule YAG laser, and people wouldn't come in my lab because they were afraid that this energy would burn a hole through it. They used the same laser to cut steel. So I was working in this lab, and my boss told me if I had an accident, they'd just take the body on out and do away with it. So these guys didn't care about me at all. So I had this laser. These guys took the laser and tried to hit Venus with this laser beam, right? And what happened, you can always hit these planets with a microwave beam, right? Turns out, when you go past the sun and try to hit a planet out in the solar system, what happens is they found out that microwaves will always have a delay. When you get close to the sun, the delay would be on the order of milliseconds. That's a drastic mistake. What happens, it turns out that this delay is a function of the microwave frequency. And however, for shorter wavelengths, that you get a microwave length or higher frequencies, you get more delay. So let's go forward. And to summarize this picture, I'm going to summarize this and I'll be done. What happens with the microwave, you get a delay with the Shapiro effect. But however, microwaves skimming the rim of the sun, you will get a light bending. This is what happens with microwaves. The question here is, if Einstein is correct, then where are the Einstein rings? If you have many stars out in the star-filled skies at night, you see all these stars, right? And many of those stars are pretty much like our sun. As far as we know, all these stars have a plasma rim associated with it. And if there is light bending whatsoever, we should see Einstein rings all over the sky. That's not there. It's not there. So what happens is, the question is, where are they? So the reality tells us that light rays are passing by these stars in deep space where there's no plasma. So there's no bending in the light at all. So let's go forward, and I'll just skip this part about the mathematics, and you can see me. This is on my website, so you can go to the mathematics, and I calculated the solar minimum energy path and the light bending, coming up with this equation that general relativity used. This is the derivation of the same equation of general relativity without relativity. This is bad news for those guys. So here's the major event that's going on at the center of our galaxy, known as Sagittarius A. This device, whatever this thing is, they estimated it's about 4 million times the mass of the solar system. So what happens is that there's an orbiting stars about this thing, about 17 some stars orbiting about this thing all along Kepler paths. This has been observed for the last probably 20 years now. And this star S2 is now on its second orbit, almost a perfect elliptical path about this thing, where the red X is. There's a supermassive object there, and there's no light bending in this thing at all. This is bad news for relativity. So what happened, if relativity were factual, this is what you should see. You should see light amplification or light scattering somewhere around, according to the textbooks. If relativity were actually the case, this Sagittarius A should look pretty much like that. You don't see this. So therefore, where is the Einstein rings and where is this scattering? You don't see it. And this is what's in the textbook. A star orbiting about a black hole should be amplified when it passes behind the black hole. And you don't see this. You see it in the textbooks, but you don't see it in space. And you don't see it in cosmology. This is what you do see. This is what you see. You see no bending whatsoever. So summarizing what I just talked about, all this stuff, so let's finish up. Just skip over to the summary and conclusion. And in the conclusion, you have the light scattering and light bending according to general relativity and all these things here. let's summarize, and then I'll finish. In summary, the gravitational gradient field of the sun acts only directly on the plasma limb of the sun, and there is no bending whatsoever outside of that. And you take a look at the whole electromagnetic waves propagated free of plasma, has no bending whatsoever. So even Einstein said in his own word, quoting Einstein, he said, with the velocity of light is not depending on the velocity of the light source, and all my theories are wrong. So I'm quoting him right now. And what he said, wenn du die Lichtgeschwindigkeit ein bisschen von der Geschwindigkeit der Licht abhängig ist, dann ist meine ganze Theorie falsch. That's what he said. I just said him his own words, okay? And this is Einstein, okay? This is it.